Hey guys, it's your favorite calculus teacher, and we're going to learn about another application of our second derivative. So the second derivative is, very useful for discovering things about concavity, especially points of inflection. But the second derivative can also be used in what's known as second derivative test, and that's what this video is going to be about. So the second derivative test is actually not about concavity, but although it is closely related to it, it's a test for determining whether a certain extrema point, a certain critical point, is a maximum or minimum. Okay. So let's say we have a function. Okay? So we have function f of x, okay? Let's make that function x squared minus 6, okay? You might know exactly what this is. This, the minimum point, but we're going to do it anyway. We have f prime of x equals 2x. And when we set that equal to 0, we get x equals 0. Now what the second derivative says is that if you were to plug in this value in your second derivative, say we have f prime prime of 0, well, f prime prime of x is just a derivative of f prime of x. So we know the second derivative will be 2. So if we were to plug in 0, we'll still get 2. So if f prime prime of c, or c is the x value of our critical point, if we were to put f prime prime of c, if it was greater than 0, it's a minimum. It's a minimum point, and if it's less than 0, it is a maximum point. If it is equal to 0, it's a dud, meaning that the second derivative test does not tell you any information. It's inconclusive. Okay, or what I would like to call a dud. Okay, now we're going to establish the reasoning behind the second derivative test. So what do you know if the second derivative is positive at a point? It means that the graph is concave up. We did this last video, right? So if the graph is concave up and we have a critical point where f prime is equal to 0, then it has to be a minimum point. Okay, you can see it's concave up. It's concave up. That means it has to be a minimum. If it is concave downwards, that means the slope will always decrease. So it will reach the 0 point and then start being negative, which means this has to be a maximum. This is a min, and the bottom one is a max. Okay, so when it's concave downwards, the critical point will always be a maximum. So if f prime prime of c, where c is our critical point, the x value of the critical point is less than 0, it's concave down, it's a maximum. What about the special case in which f prime prime of c is equal to 0? Well, it could be any. Okay, we're going to show examples of each case. So if f prime prime is equal to 0, it means that you have a potential inflection point. So I did show a graph of f of x equals x to the 4th. And this had a false inflection point. However, it is a minimum. Okay, the first derivative test does show that. It is a minimum. However, when you have a graph like this is also a point where f prime prime of c is equal to 0 and f prime of c is equal to 0. The slope is 0 at that point. And the second derivative is also 0 because this is a point of inflection. Meaning you can either have a minimum or a maximum if you were to invert the graph of this. You would have a minimum or a maximum or none at all, which means you don't know for sure, you don't know for sure whether if f prime prime of c is equal to 0, you don't know that whether it's a minimum or a maximum or a point of inflection. You just know the fact that it could, well, minimum, maximum, or neither. You just know the fact that the f prime prime of c is equal to 0. Okay, so that is no bueno because it doesn't satisfy the test. Okay, let's do a practice problem. Okay, so what I'm going to do is delete all of this. Okay, and let's try to find some relative extrema. Okay, where possible. Okay, so let's say we have the graph of f of x equals x cubed minus 3x squared plus 3. Personally, I would prefer the first derivative test since it always gives you results, but the second derivative test is sometimes quicker and cleaner. So first we need to find f prime of x. We want to find extrema, so we have to find critical points. So you have 3x squared minus 6x. We set that equal to 0, and you get, if we factor out 3x, we get x minus 2. So we have x equals 0 and x equals 2 as our potential critical points. Rather than using the first derivative test, why not try the second derivative test since our polynomial is not of a high degree? Okay, so our second derivative results in a linear function. Okay, so we have 3x squared, we get 6x minus 6. Or just to simplify things, 6 times x minus 1. Okay, so f prime prime of 0 is 6 times 0 minus 1 is negative 6. Okay, so it's concave downward, so x equals 0 is a maximum. What about x equals 2? F prime prime of 2 is 6 times 2 minus 1, which is 6. So we have concave upward, which means this is a relative minimum. So this is a way more cleaner than the number line in the first derivative test, okay? Because you just have to plug in two values into a linear function. However, a major disadvantage of the second derivative test is because that inconclusive condition where f prime prime of x equals 0. Otherwise, this is a lot cleaner approach. This approach is more or less up to you, whether you want to keep on using the first derivative test or use the second derivative test. However, if the second derivative test fails, you have no choice but using the first derivative test. Thank you. Make sure you comment if you have any questions. I will try my best to get back to you, and have a great day.